Good morning. Today we're looking at section 7.2, the Fundamental Theorem of Calculus. In section 7.1, we define the area under a curve as the limit of Riemann sums of approximations made by thinner and thinner rectangles. It's a straightforward method of approximation, but it's tedious. What we'd like to do is have an area function, capital F of x, which is the limit of the Riemann sums, which takes the area from some starting point a to x, and we'd like to produce a formula for the function f of x in terms of the formula little f of x. A minor detail that sometimes confuses students, we've gone from dx to dt because x is our ending point of the area function, and so since we've already used x, we switch to a variable t. What we're going to do is look at some polynomials where f is a low degree and use Excel and best fitting curves to come up with a formula. And then we're going to try and generalize our guess into the fundamental theorem of calculus. It has two versions and it's something that should be memorized. If we recall from section 7.1, what we looked at was the area was gotten by taking the number of intervals and increasing the number of intervals until the area looked like the area under the curve. A detail that we skipped over last time is in an interval, we can take the rectangle anywhere we want and it shouldn't make a difference. We started with the left-hand side because that made our computations easier. We're going to instead go to, in this section, making our approximations in the midpoint of the interval because that will be a more accurate area. And if we're trying to find best fitting curves and guess an area function, that's a better way to do it. So we're going to look at a series of examples. The idea is we'd like to start with a nice function, so a polynomial of low degree, find the area from A to B, and we'll start with 100 intervals. And so I'm going to start with the constant because that's the easiest. It's worthwhile to look at formulas and recall what we did. When we look at the formulas, x of n started with just the starting point, b1, and however many intervals we want across, we're doing that interval with. But as I said, that would be the right-hand rule. So the right-hand rule starts with 0 plus 1 interval. That's how high the first one was. Evaluating at the right-hand side, so 2 times the interval width, 3 times the interval width, 4 times the interval width, 5 times the interval width, 6 times the interval width. As I said, we're going to back up half a step. And so instead of xn, we'll look at the midpoint, and then we just have our function. Well, since this is a constant function, f evaluated anywhere is just what that value b was. The area of the rectangle is base times height. This is the height. The base was b7. That's our interval. And then the summed area is the area we have so far. So I'd like to plot it. And I not only can plot the initial function, which was a straight line, I can plot the area function. And when I plot the area function for the constant tends to be a straight line. And if I have a different starting point, it's going to give me a different constant there. But I'm looking at if my function f was a constant, my area function looks like k times x when I'm starting at 0, realizing that 2e to the minus 14th is 2 times 10 to the minus 14th. That's just round off error that's coming into my computations. If I try the same thing with a linear function, I'm going to look at it, and again, I do the same kind of thing, except now I'm getting my area function being a quadratic function. It looks like a good fit, and it's k over 2x squared plus m times x from that linear function. And we notice that if I change k and m, I still get that same k over 2 times x squared plus m times x. So in terms of looking at this, I've got a basic function which is linear, and the area function which is quadratic. And the coefficient of x turns into, I divide by 2 and get the coefficient of x squared, and the constant becomes the coefficient of x. If I try cubic, I'm going to look at it, and once again, I see the same basic thing going. At this point, with the cubic, I want more intervals, so I'm going to go up to 1,000 intervals. And notice, if I'd started with 6x squared plus 8x plus 5, that turns into 2x cubed plus 4x squared plus 5x plus some constant that is trying to be 0. And my hypothesis is the constant here is just my initial constant divided by 3. My constant here is the initial constant divided by 2. And we carry over the initial constant for the linear term. I'm just going to check that a couple of times and see that it does seem to work. 21. Go back to 3. This we got from the previous time, and so I'm dividing by 2. I'm going to then look at a cubic equation. What I think is going to happen is the cube term is going to turn into a 4th degree term, but divided by 4. The square term will turn into the cube term divided by 3. The linear term into a quadratic term divided by 2, and the constant into the linear term. So we're trying this with the cubic equation, and notice that's precisely what I have. I look at my interval size, so 8 turns into 2, 3, a 1, 6 is trying to be 3, and 7 turns into 7. And if I change, I have the same pattern. And so what I've established is for polynomials, we have a polynomial rule that seems to say this area function should be something that if I take the derivative of this area function, I get back to my starting function. One of the things worth noting with any of the area functions is I set up the area functions very nicely starting at 0, but I might wanted to have started at some other number like 2, and that leaves the basic area function. There's just a constant there, depending on did my area start at 0 or did my area start somewhere further out. That brings us to the fundamental theorem, and the fundamental theorem says if I want the area function between a and b, I can get that by looking at something whose derivative is the original function. We notice that if we add a plus c to our function, that will have the same derivative, so our area function always starts with a plus c. In trying to understand why this works, why the fundamental theorem works, it's useful to look back at the definition of derivative. The definition of derivative was the limit as h approaches 0 of f of x plus h minus f of x divided by h. Well, as h is going to 0, I'm getting this thin little rectangle area between the difference here. And so the top part of this is the area of this thin little rectangle. If I divide by h, that's the width. What I'm going to get is the height. And so the derivative of this ought to be the height of the function. There are two versions of the fundamental theorem of calculus. One version says, if I have a nice enough function, so f of x should be continuous on an open interval, if I wanted to find the area function, then it's going to be a function whose derivative is back to the original function. I picked a different area, a different starting point, that would give me a change by a constant. The second version says I have a continuous function on the interval and I take any function that's an antiderivative. Well, if I do that, then I can find the area by evaluating the antiderivative at the two endpoints and taking the difference of the two. So this gives us the fundamental theorem of calculus. And so they go back and forth between the two. The area function is an accumulation. The basic function, so think of this as speedometer and odometer. You accumulate from the speedometer to get how far you've traveled. The rate of change of how far you've traveled is how fast you're going. The second version says for any nice function and any function whose derivative is the original function, so any antiderivative, we can use it as an area function. This is going to set up the next several sections, which is if someone's given me a function, a formula for a function, how do I find an antiderivative for it? So that's what I'll be looking at in the next section. Thank you.